Hello everyone, we are Group 13 and today we are presenting our project Water Saver in which we hope to productionize and inspire global change in how water is valued. Our group members are Mina Saman, Evan Glazer, Muhammad Siddiqui and Muhammad Bazarbachi. In a world increasingly threatened by climate change and population growth, our team, united by shared experiences of water scarcity in our diverse homelands, has embarked on a mission to address global water distribution challenges. Our deep respect for water has driven us to develop an innovative solution centered on rainwater harvesting. We believe rainwater, a plentiful yet underutilized resource, can be transformed into a cornerstone of sustainable water management. Our project aims to alleviate pressure on conventional water sources by capturing and managing rainwater, ensuring its availability for essential uses. Inspired by the abundant rain of Florida, our initiative prompts economically viable and environmentally sound practices, advocating for a shift toward efficient, resilient, and responsible water management. Through this effort, we hope to inspire global change in how water is valued and conserved, fostering a sustainable and secure future for all. Our goals are divided into basic efficient collection and distribution, advanced integration of advanced filtration, solar power and LOT monitoring, and stretch user-friendly interface and regularity compliance. We seek to reduce overall water consumption and strategically allocate high-quality water for critical needs, prompting economic sensibility and environmental responsibility. By harnessing Florida rainfall, we aim to lower water costs, advocate for sustainable water practices, and champion environmental conservation. Our commitment is to inspire a global shift in water perception, use, and conservation, addressing water scarcity with technologically innovative and practical solutions.
Hello, starting off with the simulation. We're using Texas Instrument, and the cool thing about the ICs that we're purchasing is that they provide us with data sheets, and the data sheets tell you how to implement these devices into your design. These are the two examples that I'm providing. Of course, I'm not going to be talking about every single one, but this is how we are gonna, uh, that's how we implemented them inside of our design. So for our project, we're using two power sources. One of them is a solar panel, which is PV plus, and the battery, which is IBATT. Now, starting off, you're gonna see a capacitor from the PV plus. You're gonna see a capacitor that's connected to the ground. That's just to straighten out the DC signal. Now you have two MOSFETs that are stopping is stopping it from going through to the other side of the circuit, and it could only do that uh, if this IC on the bottom U17 allows it to go. So so you need to power on U17, you need 11 volts, and in the second pin you have charge on. So when charge on is high, it will make HO, which is gate 7, go high, which under the MOSFETs the voltage will be high, so it will short the Q6 and Q7 MOSFETs and allow the voltage to go through to the battery. The whole thing about this is that we're trying to get to the other side to charge the battery if it's needed. So we'll use U16. Now U16 is another IC that will uh, see if the battery needs to be charged. So if pin 2, if IN positive is greater than IN negative, it will output 5 volts to charge the battery. And I will talk about how we got this 5 volts and the 11 volts in my next slide. Thank you. So the question is, from where did we get the 11 volts and the 5 volts? So using our PV positive and PV positive, you have two different uh, so we're using this voltage regulator to get whatever voltage that we need. Um, this transistor is blocking the voltage to go straight through to the voltage regulator. It has to have a checkpoint to see the necessary voltage that's gonna power on our device. Because of course, if you have a 24-volt battery and your stuff only takes 8, it's gonna give you some issues. So the Zener diode is helping us out by acting like a resistor whenever it needs to. Thank God our battery it is 12 volts, so we shouldn't have any issue. But this Zener diode is gonna check if it's 12 volts, and it will allow it to go up to the transistor. The transistor is gonna short again, and is gonna allow the power to go to the 11 volts. That's how we got the 11 volts, because it's gonna, instead of 12, it's gonna lose like 0.7, and it will, like 0.7, so it will be like 11.3 volts, give or take. And we're gonna use the other one to charge the battery, the 5 volts, by using this other IC and capacitors that are connected to the ground, so you get a clean DC signal for each one of them.
So in this schematic, we can see there are so many components and ICs. So this is the booster converter, and then I'm going to talk about the U13. So we can see there's a BB plus, which is the battery source, and then I can see the C35, the capacitor, which is grounded. And what it will do, it will just smooth the DC signals. And then I can see the V in, which is the voltage input, and then the other side I can see the gate and CS. The CS is the current sampling. It just sample the current. So as we know, the gate have just two modes, which is high and low. So at 1 the gate is high, and at low, or at 0 the gate is low. So when the gate is high, it means the CTL is high, and which will make the G high, and then the MOSFET over here, which is Q4, it will short. So we can see the inductor, so the current passing through the inductor, and what inductor do is just storing the energy, and then in the magnetic field. So what it will do, the current is flowing through the inductor, and it goes straight on the down, and in down we can see two resistors, which is R2 and R3, which will reduce the resistance, and each resistor is 1 watt. So in total we have like 2 watt resistors over here. And then what if the gate is low, then it means like CTL is low, and it will make the G low. And what happened then, the MOSFET is gonna open, so there's no current on the MOSFET. So the voltage across the whole thing, the whole inductor, is gonna be like the VP plus the voltage across this point where the MOSFET is. And then that's how you get boosted. And then you can see the water. This is the water pump, and then the LEDs just tell us if the water pump is working or no. That's how we get the power on the water pump.
Alrighty. So, software design and thinking about product when it comes to building water saver, we look at this vision as a long-term play for homes, businesses, kind of anywhere to collect the water through the system. This image kind of denotes how the system would work and storage. Global water scarcity affects billions of people, from farmers to homeowners. And so really the idea of the product is to start to figure out, how do we save people money? How do we collect water and help them with utilization? How do we find ways to help them use these resources in different ways that are sustainable for the environment, and turn this into kind of a SaaS solution or more of a business solution where there's installation and then you're onboarded onto the software. So when thinking product and software design, there's a lot of technology comparisons that need to be made. On the databases side, we went through Postgres, Mongo, and MySQL. It was seeing we wanted to use a relational database, where Mongo is NoSQL. We weren't sure at first with how the sensor data was going to go and the event data, so we ended up going with Postgres because Postgres offers an extension called PostGIS that allows a geospatial capability that scales the product long term, to give us kind of that ability to look at where are the devices and ping them with future iterations. And on the back end, we went and compared Flask, which is in Python, versus Ruby on Rails, which are both kind of back-end frameworks. And we went with Flask and Python as we have I have a lot of experience with Flask and Python building those APIs as well as Ruby on Rails. But this project would be quicker to get up using Flask. On the front end, we were deciding between Vue.js, React.js, and Vanilla.js. Based on the simplicity and the skill set of the front end frameworks, went with React. Just that paradigm for React is pretty simple to get up the proof of concept for us, so that was kind of the choice. Infrastructure wise, we went with AWS versus Azure versus DigitalOcean. Even looked at Heroku, but Azure, I don't have much experience with, and DigitalOcean, I have a little bit of experience with, and it's costly when it comes to scale the droplets. AWS, we're on a free tier. That's the biggest selling point, so we can get everything up on minimal spend. The monthly spend currently is like $1 a month to keep all the instances hosted, and right now we're utilizing S3, RDS, EC2, kind of all the subnets, subroutes, NAT gateways on the infrastructure, so it's fully set up. Next, we'll talk about brand guidelines. So brand guidelines, they bring the value to the brand, and it makes it easier to maintain the quality and the integrity of what the understanding of your brand is. It gives the overall visual consistency that users will be able to say, hey, that's water saver, with the visual appearance that's consistent, and it helps to build the relationships, the business, the perception, and that's basically the journey of the user using the product is through the brand guidelines. So we've built out brand guidelines from typography, which incurs the typefaces, hierarchy, the spacing, colors with the color palette, accessibility, as well as the components, the email templates have been built out. We are using a component system called Material UX, which helps kind of build the expectation with some minor improvements of the theme provider. But brand guidelines are very important to the overall building of the business. On the infrastructure side, we have an EC2 instance here that works with Docker, and the Flask API is Dockerized in the EC2, so it's running through Nginx to do the gateway for the domain. We have Postgres database that's in RDS, which is the relational database service. And then some of the devices management is kind of relating to the Postgres and how those tables are done. And we'll come to that shortly. On the right, we have Water Saver and the domain and how that gets ported from Namecheap, where it was purchased, to then Route 53, where we create a DNS entry to CloudFront, so that we have a delivery management solution for how cache is controlled for the users. S3 bucket, which is where the distribution of the front end in React is, and then from there, S3 is configured to be a hosting domain where the users can access. And our state diagram on how we build out the entity relationship diagram here, we have users that have user information. Users have many products and have many notifications. Our product essentially is tracking device data, that device activity based on the product and the device type. And so we can then see kind of all the device activity that's happening from the event data and generate analytics based on that. And that's what we are achieving with this model as our version 1. So the webhooks API works with the device activity tracking. And so when the device is supposed to turn on and collect data, the cron job will start based on the scheduled time, and we'll check, does it have any correlation? Does it need to, did it change in value? And if so, then create that event payload, send it to the webhooks API, and that'll be through the microcontroller, and then it will have a successor error state or an exit state. So moving on to the user interface, we're using several tools such as Figma to do the design of the application, primarily focused on desktop for building the version 1 of this application. Material acts as the component system and the component library, and so the idea is that we're cutting development hours from actually building these components to our own props and needs particular to the solution, but that's channeling weeks of development that would be required, or a team to build out a component library, and then using Styled, which is a package that allows us to do theme providing to our Figma and our brand guidelines so that they can work together. So in our user interface, our application flowchart is very simple for version 1. It's, are you already a user? Yes or no, sign up. Sign up process currently is just sales team, quote unquote, reaching out to you, because this is an installation process. So if you have interest, you either call or you email. We install, we set up, and then you get your analytics on the application that give you kind of all the notifications and information of you saving water and saving money. And otherwise you're going to log in and you're going to have access to navigate your dashboard from your products, and you'll be able to see, the event management of what's coming through from your devices, as well as just some settings that are preferences to your account, and notifications on how emails will be sent. As you see here on the right, the application dashboard, you have navigation, you have search, you have filters, and you have your dashboard of metrics, which are your main analytics for version 1 that go over your water level, your battery level, the total water saved, your temperatures, how much money are you saving, and again, that event management, which is just a table of information of each device logging data. So as we move to the next user interface screen here, a few quotes: design isn't finished when someone's using it, and then rule of thumb for UX: the more options, the more problems. So keeping everything very simple, limited options, limited filtering, but getting the main minimal viable product out, is key. And then wait until users come and use it. As the board that we're programming, and we're going to use an IDE called Thani, which allows us to use a MicroPython interpreter. And Pico has a lot of MicroPython plugins for the IDE. There are also a lot of Python packages with MicroPython. And so this is set up to work with our webhooks API, which will require us to connect to the Wi-Fi. which will then allow us to do requests outside of the device. The webhook API will hit our API, log the device activity. There'll be a cron job as stated on when that's going to be scheduled and occur. And the sensors will communicate those items of data from the pins and the controller communication, and then we will utilize quite a bit of Python packages to help move the development forward faster. As there's some libraries that do like the MicroPython cron jobs and some additional Python libraries that allow us to do the communication efforts much faster and efficient.
For the battery part, we had so many different selections and choices. We can use like any kind of battery. So we decided to use the 12 volt battery, which is rechargeable. When choosing the rechargeable batteries, consider factors like capacity, lifespan, and cost. So I'm considering the MightyWax 12 volt 7AH F2 batteries, and these batteries offer exceptional charging capability up to 2100 recharge cycles and impressive charge retention. They are a valuable investment for those seeking reliable rechargeable batteries for a balance between cost and performance. Amazon Basic high performance batteries and a compelling choice. I'm gonna talk more about the MyTubeX battery. In the realm of battery selections, the MyTubeX battery was chosen due to its proven performance, reliability, and comprehensive technical information. The MyTubeX batteries offer exceptional energy density and longevity, making them ideal for our project. Their lightweight and compact design also contributes to their versatility and ease of use. And then I will talk about the power supply technology. So regarding the power supply technology, a buck converters was choosing for straightforward and cost-effective step-down AC-DC conversion. Linear power supplies were eliminated due to their larger size and higher cost. Resonant converters were deemed overly complex, and flyback converters offered unnecessary step-up functionality. In this slide, I will talk about the buck converter benefits. The buck converters provides efficient voltage regulation by stepping down the input voltage to a stable output voltage suitable for the project's components. Its compact size and high efficiency make it well suited for the integration into the project designs. The buck converter's simplicity and reliability simplify the overall system design and maintenance for the project. So the combination of MightyWax battery and the buck converters based power supply solution ensures reliable and efficient power deliveries for our project. This combination meets the project performance requirement while optimizing cost and energy efficiency.
We are using Raspberry Pi Pico microcontroller as it significantly enhances the rainwater harvesting and management system by integrating various sensors for real-time data collection and monitoring, managing pumps and valves for efficient water distribution, and ensuring the filtration system meets required efficiency standards. It optimizes energy use with solar power integration and maintains low energy consumption. With wireless communication capability, the Pico enables seamless data transmission and remote monitoring, supporting a user-friendly interface for easy system control. It processes data in real time for predictive maintenance and compliance monitoring, ensuring regularity adherence. The Pico modular design allows for scalability and customization, making it adaptable to different environments while its robust performance ensure reliability and durability. We choose the Orbit 57069 rain and freeze sensor and the Yearlink LoRa Smart Water Level Monitoring sensor for our rainwater harvesting and management system due to their reliability, perception, and advanced features. The Orbit sensor is designed to detect rain and freezing conditions, automatically adjusting water collection and distribution to prevent system damage and optimize water use. The Yearlink sensor provides accurate water level monitoring with a wireless battery powered float switch, making it ideal for remote or hard to reach installations. The LoRa technology ensures long-range communication and minimal power consumption, while the required dual-link hub allows for robust LOT integration, enabling real-time monitoring and control. These sensors collectively ensure efficient, safe, and effective rainwater management, aligning with our project goals of sustainability and advanced technology integration. To improve our project, we need to install larger capacitors along with the installation of two fans to cool down the PCB will significantly enhance the overall performance and reliability of the system. The larger capacitors will provide enhanced power stability by smoothing out fluctuation in the power supply, reducing energy loss, and extending the lifespan of electronics components. They will also improve energy efficiency, protect against power interruptions, and optimize system efficiency, ensuring constant operation even during variable conditions.
For the project status, challenges, triumphs, we did the project kickoff in January. We met as a group and collaborated on the idea and what this project could look like. Then we worked on the project scope in February, scoping what we could accomplish. March, continued that project scope and started to draft the initial documents and requirements from the research on the project. Then we went into project review in April and began to finalize the scope and demo to the professors, and start to begin some of the development. But May is really where the project started here in Senior Design 2, where we really began to focus on implementation efforts and getting a working prototype. Something that we saw in May is that there's going to be some time constraint challenges for the short summer semester. But we're working through kind of the initial development, and June has really been prototyping, and we'll continue to be prototyping until the midterm here. But the PCB is built, the battery and sensor are in testing. We're testing out loading the code onto the Pico board, and the website is live at watersaver.app. Our AWS infrastructure is configured. All this, the NAT gateway, security groups, the VPCs, the services, it's all configured, and the UI and API are already in development, with some of the initial components in play, so that we can start to track the device activity. So very much feel like the project's moving in a good place. Lots of questions, lots of moving parts and pieces that we still need to figure out, but we're definitely on track. So the budget in this project, we are on track. We aren't nearly at $548 like we thought the estimated value would be. We are very much at half of that. I don't think we're going to need every item that we had scoped in requirements, but we are still working on that. We do think inventory wise, we will need to order more embedded controllers of the Picos. It just depends when we go to connect them to the sensors, what that payload is going to look like and the resource required. So that's still in discovery for us, but we have enough pins on the PCB board to acquire some more Picos.
WaterSaver is not just a technological marvel, it's a testament to the power of teamwork. This project brought together electrical and computer engineering students to work on a single project, not only to apply the knowledge gained in their degrees, but also to develop their teamwork skills. Working as a team presented valuable lessons in the time management, communication, and importance of regular meetings to ensure everyone is aligned and to minimize mistakes and missed deadlines. Additionally, teamwork enriched the final project by incorporating diverse perspectives from each team member's background. Through the effort, we were able to develop the Water Saver, a system that can significantly impact water conservation effort around the world. Water Saver can be particularly beneficial in third world countries where water conservation is vital. These regions often experience water shortages, leading to days without water, which can contribute to the widespread disease and even facilitate in the world. Thank you.